Yeah, yeah, yeah. Yeah. All the work is just creating the IP project, temporary project, and all your hardware knowledge is within the IP. It's just a matter of once the IP syncs correctly, then you just, generate the IP and run it in your project, and then, run your bit stream and all that. Yeah, all your work goes through here. Yeah, you don't worry about that. Just make sure the microflash is ready for you. What? For which one? Yeah, for this one, you just write it. Um, I think they give it to you. I think it's M level like M33.
Okay, sorry about that, guys. My computer literally crashed right as I started up the lecture. So let's hope it's not the lecture and it's just something else that went wrong. Okay, so 18th lecture, and today we spent what how many lectures has it been since we came back from break? It was 3 lectures. So we spent 3 lectures talking about unsupervised learning, basically training all sorts of complex deep neural networks. So now we're going to talk a little bit about unsupervised machine learning techniques and the techniques that we need to implement those techniques. So first things first is that we are going to start off by discussing this thing called principal component analysis. Okay, so we'll introduce it, methods to derive the principal components, and just the usages of principal component analysis. And that will be that for today. So nice light. Well, it's not light. Well, you'll see. So let's start off with the motivation. So the motivation behind PCA is simply dimensionality reduction. So if we have a given data point that has n dimensions, we would like sometimes to reduce it to something far, far less than, or I should say d dimensions. We would like to reduce it to something far, far less than d dimensions. So for instance, the MNIST data sets that we use so frequently, it's a 28 by 28 image. It has, constantly get this wrong, 784 pixels, I think. So the dimensionality of those images are 784. So, that's okay. Like, there's nothing wrong with it. But, it'd be nice if the images, if the inputs were less complex, right? I mean, we would like do we really need 784 quote-unquote dimensions to represent a handwritten digit? Maybe yes, maybe no. So there's this huge motivation behind trying to get complex data that has d dimensions and try to reduce it to data that has, d over 2 dimensions, 10% of d dimensions, right? And so there are multiple motivations behind this. First is the often named curse of dimensionality, which is simply that if your data is 2-dimensional, then it can make learning tasks more difficult because as the number of features increases, the available data becomes sparse, which means the distance between data points is less meaningful, which can harm a lot of algorithms. Oh, I'm going to stop correcting this, but you guys should correct me. Maybe I should put that as extra credit on something. So, I mean, what's the highest dimension? What's the highest dimension? Let's say we want to encode the English alphabet. English alphabet, and only lowercase letters. Let's ignore extended ASCII and all of that, and capital letters and all of that. Only lowercase letters. What's the reasonable maximum number of dimensions we need to represent the English alphabet? What's the maximum vector size? That's within reason. I mean, of course, we can make the vector size infinite and be like, oh, the last infinite minus so on dimensions are all zeros and stuff like that. I mean, there's a trivial. But what's the maximum dimension size that's not trivial that we can use to represent a alphabet? Yeah, please, Ben. Yeah, 26, right? 26 letters. And then we could just say each one of the dimensions in the vector represents a particular character, right? So that's fine, right? That's fine. But there is a drawback, and the drawback is that because your dimensions of a particular feature, in this case, the dimensions of the character, is so large compared to the possible values of the character, basically the model will know nothing about the relationship between the two characters. It will consider basically A and Z to have the same distance apart from each other. It'll consider A and Z to be the same distance apart as the distance between A and E. Now, is that necessarily correct? I would say no. Like A and E have things in common. They're both vowels compared to a vowel and a consonant. A and E are used much more than Z. So that seems like it doesn't seem like a logical embedding to have those things. It doesn't seem like an ideal embedding to have those two letters basically be the same distance apart as the other two. But it is useful in certain cases, right? So now extend this idea up to, an image, right? Where instead of representing each pixel, where instead of representing an image as a collection of pixels, you literally represent an image as a permutation of pixels. Every single image, every single space in the vector represents a separate permutation of pixels. And so every single space in the vector is basically a one-hot encoding of a particular image. Now, would that be useful? Probably not. Probably it would be impossible to run on any machine. But also, the machine will pretty much just see, okay, there's one image here. Even if two images are of one, just written slightly differently, the machine will still see those two images as the same distance apart as image of a handwriting of 1 versus the image of handwriting of 3. So that's what people refer to as the curse of dimensionality. If there's too many dimensions in your network, if your network is too wide, if your embeddings are too much compared to the complexity of your data, then it could actually harm the model. Then the model, again, the model's trying to cheat. It's trying to get the lowest possible loss possible. And so if you have too much of a feature space, it'll just be like, okay, all the ones go into these feature spaces, all the 2s to go into these feature spaces, all the 3s go into these feature spaces. It'll separate them out too much and not even bother to look for similarities. The model only forces itself to really learn or understand something when it's constrained. If it's not constrained, it'll just phone it in. It'll be like, well, I have brute force available to me. Why bother? And it's not unreasonable. That's not an unreasonable thing. If you have an infinite amount of money like Elon Musk, you're of course not going to clip coupons and go to Meijer, right? But also, that's not what we want. We want the machine learning model to actually learn something, so we need that constraint. So you can't just make the variables too wide. We can't make layers too wide. We can't make embeddings too wide. We have to constrain them in some way. So that's the basic idea behind the curse of dimensionality. Just the simple way to put it is giving resources to a computer, if it exceeds the complexity of the data, could often harm the computer rather than help it. Other reasons for reducing the number of dimensions in your data. Avoid overfitting. Very, very similar to the curse of dimensionality. and we've discussed that many times before. Improved computation efficiency, again, like one-hot encoding for all possible images and NNIST is computationally infeasible. So yeah, so we have to reduce, so reducing the number of dimensions for data, of course, reduces the resources needed to compute to run a neural network model. And noise reduction is a big one. Basically, if you reduce the number of dimensions, again, you're forcing the computer to just learn, to just keep all the salient features of a particular data, right? You're basically forcing the computer to just keep, if it's looking at, for instance, a digit of 1, you're forcing and you're reducing the dimensions, you're forcing the computer to simply say, okay, I want to make sure I preserve that line. That's the first thing, ideally, that I want to preserve. The rest of it, let's say it's in a noisy background, there's a lot of static, it's not going to bother, hopefully, it's not going to bother preserving. So you reduce the number of dimensions, get the image down, shrink the image, get the digit, and then you could, of course, upscale the image later and make it so that the noises, and make it so that it's the same size as the original, only in this case, once you downscale and then upscale, it basically helps eliminate a lot of the noise. And the other, but the most important, like, I mean, not the most important, but the most common reason you'll see for dimensionality reduction is visualization. You see this a lot. PCA, TSNE plots, if you've seen those before, this is simply the idea that you want to reduce a complex data into a two-dimensional plane to make it easy to view, right? To make you sort of the relationships, the distances between the different types of data easy to view. So there's actually a kind of famous example here where Andrej Karpathy trained a convolutional neural network. Trained a convolutional neural network to embed the images as some dimension. I forgot, some dimensional embedding. And then I think it was, I want to say it was around on the order of 1,000, but I don't remember completely. But he got some dimensional embedding, and then he reduced that number of dimensions to 2 dimensions and then pasted the picture. So if you see, he pasted a picture, and he pasted a picture on the point that 2-dimensional dimension represented, right? So if you see, if you go through this collage, his madness, there you go. Okay. If you go through the collage, you could see that's actually doing this, reducing the number of dimensions to get sort of the point where you should paste the images results in similar images getting pasted very close together. So for instance, the images with black dots are pasted very close together. Some marine life images get pasted close together. You could spend days in this whole thing. Pictures of ships get pasted closer together. Fitness get pasted closer together. Children, etc. Okay. Kind of a neat thing. This got him a lot of fame back in the day. I think he's the director of AI at Tesla now. So yeah, so that's another reason for dimensionality reduction. You just want to be able to visualize the data. You want to be able to see, okay, what data points, if I do embed the data as two-dimensional in a particular vector, are the pieces of data that look similar are the pieces of data that look similar closest together? And so it's a nice way, so that you see this a lot when you actually want to create embeddings for your machine. You want to create machine learning. You want to create machine learning models that actually embed complex data as n-dimensional vectors. I mean, you could do a whole sort of distance analysis, get one example, see what the closest vectors to that distance, to that example are, and so on and so forth. Or you could paste a bunch of examples on a 2D plane and and see if the examples that are most similar get pasted close together, and if the examples that are very dissimilar get pasted close to far apart. Okay, and it works roughly well. So that's the idea behind dimensionality reduction. We just want to get to a point where we could reduce the number of dimensions in the data, but we want to keep sort of the salient information. Okay? Of course, we could reduce the number of dimensions by just picking the first two dimensions and calling it a day, right? But probably that wouldn't preserve a lot of the important salient information that makes the data, right? So we still want to keep sort of that. We want to keep those features, the thing that keeps the data, that makes the data the data. But we also just want to be able to compress those features in a smaller feature space. So question is, how do we do that? So let's first construct a artificial example. And yep. Okay, so this just gives us an artificial example here, and if we plot it, actually, and this is just sort of a plot function, and if we plot it, so let's look at an artificial example. Mainly, we want to find ways to project. We want to find ways to project a data of dimension d onto as a projection of dimension d minus 1. So what does this mean? Let's say we have some data. We have some data here, and as you notice, this is artificially created data. We have two major clusters that I plotted here. Just a cluster centered around 2, -2, and then a cluster centered around 2, 2 with a covariance along the xy line. So we have the data in the blue lines, and so we want to. So this data is two-dimensional, right? Every piece of data here has two values associated with x1 and an x2. Okay. Now we want to make this data one-dimensional. We want to reduce the number of dimensions. So how do we do that? Well, if we remember from linear algebra, 2 dimensions is a plane. 1 dimension is a line, right? So what we're saying is when we want to reduce the data from 2 to 1 dimension is that we want to basically take all the points that are on a plane, and then we want to represent them as points on a single line. Okay? So if we choose the line correctly, this might not be too bad, right? So the most important thing about this data is that there are 2 clusters here. Okay? So let's say we choose a line like so that runs through the data. The line is 1, 1. And so for every data point, we just project this data point onto this line here. Okay. So if we do that for all the points here, we are left with something like this. We are left with something like this, which is the representation of the 2-dimensional data as a one-dimensional object, Okay? And this seems to work. This seems to work mainly because it seems to work in the sense that the major feature of the data was that there were 2 clusters, and even though we got rid of some aspects of the data, I mean, if we wanted to reconstruct it, we wouldn't be able to get back these little red lines. But we do still maintain the information that there are 2 clusters in this data set, right? That's the salient feature of the data set. So choosing a line correctly that goes through the data set that we project all our data points onto keeps that information there. Okay? So that's a good thing. Now, on the other hand, What if we chose our data point badly? What if we chose the data point badly and reduced the data points? In reducing the data points, eliminated some crucial information. Well, let's just go with that. Let's choose quote unquote a bad vector to project the data points onto. And let's just choose the perpendicular vector to the one we had before, basically 1, -1. And so we do the same process as before. We take each data point, we project this data point onto the vector, onto points on the vector. Okay? And we're left with a particular distribution. We are left with a distribution here. And we are left with a histogram. Okay? So, which vector is better? To me, it seems like the first vector is better because this vector, we chose this vector, and right now this vector is representing the data as basically a roughly Gaussian curve centered around 0, right? But that's definitely not the data when we look at it from the two-dimensional plane. From the two-dimensional plane, the data has 2 clusters, 2 peaks, right? So it makes more sense to represent the data using this vector, because at least with this vector, this gives us 2 peaks, and it still gives us information, a big piece of information about the data set, namely that the data point has 2 clusters. Okay. So that's what we want to do. We want to basically be able to reduce the number of dimensions, and in order to reduce the number of dimensions, we need to choose a vector or a matrix that when you project the data onto that vector or matrix, you preserve as much information about the data set as possible, as much characteristic information about the data set as possible. Now the question is, how do we do that? I mean, besides looking at the data, because I mean, we have things to do. It would take us millennia to look at all the data sets and try to come up with the vectors that allow us to reduce the dimensionality of any given data set. So the question is, how do we do that? Well, if we look at the two 1D distributions here, okay, this 1D distribution of projected points has a variance of 4.56, and this 1D distribution has a variance of 0.1-ish. Okay, so the variance of this data set is the variance of this projected data set is much smaller than the variance of this other projected data set. So what does that mean? Well, it means that really what we want is to maximize the variance of the projected data set. Not just the variance. We want to maximize the variance of the projected data set. And so when we do that, there's a pretty good chance that we are going to preserve essential information about the data set, right? So the variance of the maximum variance occurs when all the data is spread out as much as possible along a lesser dimension. Okay? So that's what principal component analysis is. Come on. Principal component analysis is it's simply the idea. It's simply the central idea behind principal component analysis is that we want to reduce, or we want to maximize the variance of the reduced points. There's a second interpretation of principal component analysis that we won't get to, which is that we want to preserve as much information as possible to make the reconstruction of the original data easier. These two interpretations are are pretty much equivalent. And if you want to look there, I put references for deriving PCA for the second interpretation in the notes. But we're just going to focus on the first interpretation and try to derive how we do PCA by simply maximizing the variance of the reduced points. Okay, so essential math skills we'll need to basically derive PCA. First is matrix calculus, which we've covered extensively. The two big ones are the derivative of x transpose x, where x is a vector, is equal to 2x. We've seen that before. And then also the vector sum reduction, which is simply that the derivative of the sum of x is simply equal to 1. This is tangentially related, but not necessarily directly. Directly appears in the derivation, but it does help under certain interpretations. Other math skills that we need. I want to put these on, of course. Other math skills we need, eigenvalues and eigenvectors. Basically, most of you have probably gone through this, have definitely gone through this before. Eigenvalues, you'll never get away from them. It'll just curse your life from the day from your college days onward. But just as a refresher, the eigenvalues and eigenvectors, we say that a vector v is an eigenvector if for matrix A dot v is equal to some scalar value dot v. Okay? So the idea behind the eigenvector is that v is a special matrix, so that when you transform v using A, when you transform v using A, it only scales v by a factor of lambda. It doesn't change its direction. And then eigenvalues are found so you find eigenvalues by solving the characteristic equation, namely A minus lambda I, the determinant A minus lambda I is equal to 0, where I is the identity matrix, right? So you guys have probably seen this in linear algebra lots. This comes up again and again. Luckily, we have PyTorch and NumPy and all these things to give us the eigenvalues and eigenvectors for us. But it is still important you guys remember, like conceptually, what eigenvalues and eigenvectors are. I highly, highly recommend a YouTube channel named 3 Blue 1 Brown, the best math YouTuber I think I've ever seen, and he has a great video on interpretations of eigenvalues and eigenvectors. I personally watch it every now and then just to refresh my conceptual understanding. Okay, so eigenvalues, eigenvectors we need to know, and then Lagrange multipliers. So Lagrange multipliers, I'm not sure if you guys have seen this before, but just as a brief intro to Lagrange multipliers. The Lagrange multipliers are used when you want to optimize a function, but you have some constraints that you need to adhere to. Okay? So remember, in the beginning of this course, we had lots of complex functions that we just put through gradient descent, and then we optimized it, right? We minimized it, whatever. We minimized it. If we wanted to maximize it, we just multiplied the function by negative, whatever, right? But the thing is, we didn't have any constraints. What if the constraints is one of the values needs to be equal to, one of the values needs to be, what if the constraint is two of the inputs need to always be in the inverse of one another? Something like that. Or what if two of the inputs always need to be equal? No, that doesn't make sense. What if the idea was that two of the inputs always need to have a normal, always have to be unit normal? That's a good one, right? So if we have those types of complex constraints, it becomes very hard to optimize a function and then constantly check to make sure it isn't violating a constraint, right? That sort of logic doesn't work very well. You have to do both things concurrently. if you want to have a chance of it working. You either solve it symbolically or you try to make both things work. So Lagrangian multipliers, or Lagrangian multipliers are simply the concept that you could basically put both the function you want to optimize and its constraint inside a single loss function and then optimize that. That's the idea. Okay, so basically with Lagrange multipliers, you develop this loss function that's simply the function that you want to optimize minus lambda. This is a Lagrange multiplier. This is a multiplier times the constraint. Okay, so in the case of x plus y have to be equal to 1. The constraint is simply x plus y minus 1 is equal to 0, right? The constraint has to always be something is equal to 0. So the total function would simply be the function you're trying to optimize minus the multiplier times the constraint. Okay? So once you have this loss function, well, how does that help you? Well, it helps you because if you optimize this function with respect to x and y, you optimize this function, and you optimize this function here. You optimize this whole thing together. If you optimize this function with respect to lambda, then you optimize for the constraint here. Okay? So you are effectively turning a variable, you're turning a function that you need to optimize, a continuous function, and a constraint that could be continuous, could be discrete, could be whatever. You're turning that into a single function that is optimizable. Okay? So that's the idea behind Lagrange multipliers. That's all you really need to know for the moment. If you want to know more, there's, again, Casual Science is a pretty good YouTuber that covers some more advanced mathematics. So highly recommend, I recommend his videos also. The Wikipedia entry for Lagrange multipliers isn't bad either. But Lagrange multipliers, the major reason we didn't go over it is that it's often used in dual optimization. So in many other machine learning courses, if you go over dual optimization, you'll get exposed to Lagrange optimizers then. We didn't go over dual optimization for the sake of time. So you're just going to have to be okay with this vague conceptual understanding, and then study on your own if you want to know more. Okay, good. So those three things that we need to know: matrix calculus, eigenvalues, eigenvectors, and Lagrange multipliers. So let's go and try to derive principal component analysis. So principal component analysis, let's talk about projections and the notations we will use. We want to project a data point that is of dimension d onto a new point of dimension which is of dimension m. Okay, so for instance, I'm going to make you bigger. How about that? Yeah. And I'm going to make you bigger. Yeah, good. So for instance, up here, similar graph, although this is well, not hand drawn, this is like computer drawn, versus the graph graph generated by Python. But a similar thing, just to get some ideas. We have a couple data points. These blue points are the datum. And so this green point is our vector. And so we simply want to project the data onto the vector, onto a new point of the vector of dimension m, where m is less than d. So for instance, two-dimensional data gets projected onto one-dimensional space. Okay? So let's define m projection vectors. Okay? So to define this new space, we need a series of vectors. So a two-dimensional space is defined by two vectors. A one-dimensional space is defined by one vector. A three-dimensional space is defined by three vectors, right? So let's define a new m-dimensional space by having m vectors, okay? And each of these vectors are of dimension d. And so because these vectors are of dimension d, It'll allow us to go from a d-dimensional space to an m-dimensional space. Okay? Hopefully this is sort of bringing up some of your linear algebra knowledge that you've tried to keep repressed for so long. So let's say the vector. So let's assume two other things about the vectors, namely that the vectors are of unit length and the vectors are orthogonal. Basically, that multiplying the two vectors together will give you 0. All the vectors, we're just assuming, are 90 degrees, are separated 90 degrees from each other, which is reasonable, I think. So using a projection. Using the projection vectors, we know that the data points xn can be projected onto the mth dimension of z. We'll call this projected point z. And we know that using projection vectors, we know that the data point can be projected onto the nth dimension of z using the corresponding projection vector transpose multiplied by the data point. Okay? Makes sense. Same thing as you did in linear algebra. We're just changing this. We're just changing the space of the space of the data. So by doing this for every dimension, we get a new vector, which is z. Okay. By the way, this parentheses n is simply the nth data point. Okay. So first data point, second data point, third data point, fourth data point, fifth, sixth, seventh, nth, eighth. So in this case, n will be 8. Okay. So that gives us doing this for each of the m dimensions gives us a new data point z. Gives us a new projected point z. Okay. Everyone with me so far? This is a lot of notation, but I'm sure I promise it'll come together very soon. So we have a way to go from x to z using m projection vectors. Okay. So we could simplify this a bit. We could write this as matrices. Basically, we simply say each of the components of z is equal to w, the projection vector, times x, not xc. Why is the c there? Because I copied and wasn't paying attention. Bad. Okay, so each of the components of z is equal to the projection vector times x. Or another way to write this is simply that we could have the projection vectors as rows in a matrix, and then we could have x simply be a vector, right? A vector of size d. So in order to get the projection point z, we simply multiply it by this matrix, the transpose of this matrix w times x. Okay. So when we do this, this row gets multiplied by this, gives us z of 1. This row gets multiplied by this gives us z of 2, etc. Okay. Make sense for all that? And so another way to write this, so this is the transpose. Another way to write w, basically the projected space. The transformation matrix is where every column represents a new projection vector. Okay, this is just to keep things consistent with the PyTorch library we'll use for PCA later on. Doesn't really make a difference if you use rows or columns. You just have to make things work. Okay, so a note on reconstruction. So what are we doing? So this projection, we use that matrix W, or we project this data point, we project these data points onto a lower dimension, a dimension of size 1, using the matrix W transpose. Then in order to quote-unquote reconstruct the data, we could use that matrix W to simply multiply matrix W by the projected point Z to get a reconstruction of the original data. Now, Now, the reconstruction won't have all the information as the original. I mean, this is a lawsuit process. There's no way to keep that information because you're reducing the amount of information to 1, so something has to disappear, namely these red bars disappear. So these red bars disappear, so when you go back, basically all the points will be on this vector, but, you know, it'll be close by. So in the 2D space, it'll still have some of the characteristics that you were looking for before. And in fact, as you go to higher dimensions, say you were reducing from a dimension of, you reduced from a dimension of like 1,000 to a dimension of 500, and then you reconstructed the image, it actually works pretty well, the reconstruction. At least for a lot of visual tasks. Yeah. So that's how we reconstruct the data. That could be useful later. That will be useful later. So now let's talk about principal component analysis. So we want to find the projection vectors, right? We can't choose them manually. It's too much effort. So and it's not programmable if we choose them manually. So we want to find the projection vectors, but what should the criteria be? Well, the criteria we're going to go with is that it seems like the projection vectors are best when the variance is maximized. So let's try to focus on that. Let's try to find the projection vectors where the variance of the projected points are maximized. So how we do that? We simply calculate the variance of the projected points. This is a common formula. Again, linear algebra, it's never leaving you. So we get the variance formulation, and simply we assume that the data has been normalized. That's a pretty common thing you do with most data. You normalize the data so that every dimension has a 0 mean. So the projected points should also have a 0 mean. So in this case, we know that this disappears, and so we get simply the projected points, which is equal to W transpose X. Okay? So then we go from, so then the variance is simply 1 over n for the sum of W transpose X squared. We could simply rewrite this as W transpose X times W transpose X, and then transpose, and then all we need to do is simply, we could optimize this a little more. We could take the transpose of this. We could take the transpose of the inside. I missed, oh, it's right here. W1. There. That's what I wanted. Okay, there we go. I was like, where's the W1? All right. So we could just simply rewrite this. The Wx squared is simply can be written into Wx times Wx transpose. So then we simply take the transpose of this. When we take the transpose of the multiplication of two vectors, what happens? We reverse the order of those two vectors and take the transpose of each of those vectors themselves. So we take W1 transpose, we put it to the outside here. We take X transpose, we put it on the inside, and we take the transpose of that. Then we have X times X transpose. And so we get this little formulation here. This little formulation here. And this little formulation is the covariance of the matrix, the covariance of X, the original data points, assuming that the original data points were normalized and had a 0 mean. Okay, if they weren't normalized and had a 0 mean, there's a minus mu term that goes in here in a normal covariance calculation. But we're still assuming that we normalize the data points. So this whole thing here is simply the covariance matrix of the original data points. Okay, and we denote that using the symbol sigma. And that is upsetting to me on so many levels because it makes things so much more confusing. I'm sorry, but this is like what people typically use. They use sigma to denote the covariance matrix. So I'm gonna stay true to, you know, I'm gonna bow to peer pressure and keep that notation alive. but you have to remember this is a covariance matrix. This is a summation symbol. Yeah, that's upsetting, but it is what it is. Okay, so the whole thing together, the covariance, so what does this all mean? The covariance of the projected points is simply equal to the covariance of the projected points along each dimension is simply equal to that dimension's projected vector transpose times the covariance of the original data times again, the projection vector corresponding to that particular dimension. Okay, pretty interesting result. Basically, you're transforming the covariance of the covariance of the projected points can be easily calculated from the covariance of the original data points. So how does that help us? Well, all right. Well, it helps us because we can use Lagrange multipliers. Why do we need Lagrange multipliers? We need them because we need to make sure the unit vector of the projected vectors stays equal to 1. Okay? If we didn't have this, then maximizing or minimizing this function here becomes trivial, right? Minimizing or maximizing the variance if the projected vectors don't have to be equal to 1. We just make the projected vectors like infinitely long, and it just creates and it maximizes the covariance that way, right? So we need that additional constraint that the projection vectors are equal our unit length, but we also want to maximize the covariance of the projected points. So what do? We write a Lagrange equation. And simply because we do everything because we write these functions, we use PyTorch and PyTorch automatically assumes we're minimizing things. So instead of saying we want to maximize the covariance, we say we want to minimize the negative of the covariance. Same thing. Ends up to be the same thing. Then we add in the Lagrange multiplier for the constraint, namely that the vector times itself has to be equal to 1. Or also known, the vector times itself has to be equal to 1. Okay, easy as that. And then we also get our results from the previous slide to simply say that the covariance of the projected of the vector is simply equal to w times w, the wi times t times the sum of times the covariance matrix. Oh, this is why it's upsetting. I knew I missed it somewhere. Times the covariance matrix plus lambda, and then if we minimize the function, and then we simply have the Lagrange equation, we could simply minimize the function with respect to the projection vector, and doing so gives us that the covariance matrix times the projection vector is equal to lambda times the projection vector. Okay? So what does this mean? This means right here that this is hearkening back to our eigenvectors, right? That a matrix times a vector is equal to some scalar times a vector. So reorganizing things a little bit, multiplying the left hands of both sides by the transpose of the projection vector gives us that the covariance of the projected points is equal to lambda, the eigenvalue, the maximum covariance occurs when the covariance of the maximum of the sorry, I lost my train of thought. The variance is maximized when the projection vectors correspond to the eigenvectors of the covariance matrix. Okay, so when we want to find our projection vectors, we just need to find the eigenvectors with the largest eigenvalues. So then, let's do that. Namely, let's do that. And so, what does that? Let's go through the actual process of principal component analysis using everything we've learned. first we need to normalize the data, right? We need to make sure the mean of the data across every dimension is equal to 0. This is simple to do. Well, it's simple to do using for loops, but NumPy or even Torch gives you a nice mean option, which allows you to calculate the mean across for a particular dimension. And so, easy, calculate the mean of the data, and you could plot it here. Doesn't change a lot, especially because I generated 2 clusters. One was around -2, 2, and one was centered around 2, 2. I mean, that doesn't, so the mean of them is going to, of course, be equal to something close to 0, 0. But, stochasticity, it's not perfect, so you still have to calculate. We still have to normalize the data this way. Okay, so first step, normalize the data. Second step, calculate the sample covariance matrix, and all we need to do there is simply, all we need to do there to calculate its covariance matrix, the standard linear algebra equation, we just take the sum of all the data points, multiply them by their own transpose, and then add them together. We could do this in matrix form. Just take all the data points as a matrix, multiply the transpose by itself, then we should get a d by d matrix and divide that all by n to normalize it. But thankfully, Python gives us a nice little function to do that easily. Well, we could do it manually. We could do matrix math manually, or we could just call np.covariance or torch.covariance, calculate the covariance that way. Either way is fine. Up to you. So we calculate the sample covariance matrix. Then we find d eigenvector pairs. Okay, so we need to find the d eigenvectors that correspond to the largest eigenvalues. So we could do this by hand. Do you guys want me to sit down and calculate eigenvalues and eigenvectors by hand? Were you guys forced to calculate eigenvectors and eigenvalues by hand, out of curiosity? Yes? Okay, so you've been traumatized enough. Then we don't have to do that. We could just call, both Torch, again, NumPy and Torch are pretty much very similar. They have most of the same functions, including the eigenvector and value function. So we could just call linalg.eig on the covariance matrix and get the eigenvectors there. And the eigenvectors we do get, we have for an eigenvalue of 0, like 0.2, we get for one eigenvector, the eigenvalue is 0.2, and the eigenvector is basically -0.7, +0.7. And the other eigenvalue is 9.2, and the eigenvector is -0.7, -0.7. Okay, so unit vector, xy unit vector versus x negative y unit vector. Those are the same two vectors that we saw earlier in the lecture, right? So hints. So if we choose the m eigenvectors corresponding to the highest eigenvalues. Again, remember m is the dimension we wanna reduce to, right? So m is some number less than the original number of dimensions in the data point. So m in our case is 1. So we just need to find the one eigenvector that has the highest dimensions. One eigenvector that has the highest eigenvalue, sorry. So again, argmax, just choose that eigenvector using argmax. And then we project the data onto lower dimensional space. Same graphing function I used in the beginning of the lecture. And yeah, seems to work pretty well. It's basically xy, right? Doesn't matter if it's -x, -y, or +x, +y. The negatives just sort of even out. And you get the exact same graph that we saw, and the variance of a roughly 4.5. Okay, so it seems to work pretty well. Or, we could just use PyTorch, save ourselves a lot of hassle. We could just, there's a PyTorch function called torch.pca lowrank that gives us a lot of information, but this V matrix gives us the actual eigenvectors that you could select from to get the principal components. So by the way, when we do this analysis, the largest eigenvectors, we call those the principal components of it. So that's why it's It's called principal component analysis. Um, so we could do things this way. Again, it's very, 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 very easy. Yeah, so this whole function makes things much easier. You get the same exact value as doing things semi-manually. So that works. So yeah, on a side note, that you'll notice that the torch.pca low rank outputs several vectors u, s, and v. It outputs all these values simply because there is a technique called singular value decomposition in linear algebra that allows you that reduces a matrix into a rotation. That reduces a matrix into a rotation, scaling, and reflection matrix. Did you guys do singular value decomposition? Oh, so you got this all unlocked. All right. So you guys all know what U, S, and V are. If you don't, I highly recommend you look at Wikipedia. Wikipedia actually has a good article on it. Also, the reason it comes up in PCA is not too difficult. You could look at, I'm not going to go over it, but you could look at Herman Kemper's excellent PCA lecture. He'll go over the relationship between PCA and the SVD algorithm. Okay, so last thing. I know that was a lot, but now hopefully you understand how PCA works. All it's doing is finding basically lines in the data sets that maximize the variance, that basically get features that that contain some special information about the data. And basically, every eigenvector is orthogonal to each other. So every eigenvector contains a different piece of data or different feature it's measuring for. And then you combine a bunch of those eigenvectors together to get the original data point, to get sort of a projection of the data that is in a reduced number of dimensions than the original data itself. So going over what PCA is good for, at the beginning of the lectures, we saw Karpathy's massive image collage. That is beautiful. Basically, just sort of using PCA to find two-dimensional points for every image, reducing the number of dimensions for every image down to 2, and then pasting those images across a 2D plane, and then seeing if the similar images come closer together. We could do the same thing. We could do the same thing here, which is simply take the MNIST data set. We'll take our MNIST data set. We won't contain like all 80,000 examples. Let's just get 50 examples from each class. And then just, average out the images. We get the number of samples. Oh yeah, we average out the images. We go through that process, but more importantly, we just call torch.pca low rank. And we ask it for the 2 largest principal components, and then we transform those images. We plot each of those images according to those principal components, and then if we plot it on a 2D scale, we see that just running PCA on the data itself, right? On the data itself, no computation involved, allows us to see that a lot of the similar images are grouped close together, which I think is kind of cool. This is literally no machine learning. This is all sort of analytical math. We're just sort of segmenting the images by how they look, and what their pixel representation is like. And you see, for instance, ones are grouped closer together. Ones are grouped together. Zeros are grouped close together. 6s are grouped close together. 8s are grouped sort of in the middle. 3s are grouped basically interspersed with 8. That sort of makes sense. A 3 sort of has the same shapes as 8. So that all looks pretty cool. So what's important here, the one difference between what I did, in Karpathy's Karpathy's image is Karpathy first trained a convolutional neural network, and then took the last hidden state, I want to say, and then did PCA on the last hidden state. And then he got that big collage, okay? So that's still doing a lot of computation, but what you're doing, basically, you're training a network to sort of differentiate images, and then you're extracting those features, then you're running the PCA and lowering the dimensionality even more, and then getting that plot. This is way, way more basic. This is so much more basic is that we're just basically taking the images, taking the pixels, just reducing the dimensionality directly, and just plotting that. So if we wanted to make this even better, we could possibly initialize a random linear matrix, and then do PCA on one of the hidden states, on the the last hidden state, and see what happens. That's what a lot of people do. That's how embeddings work. So kind of cool. Also, one other thing I wanted to show, kind of a famous example. So why not show it? Come on, what are we doing? All right. One thing that's kind of neat to show is what eigenvectors are actually doing. Actually, let me just exit out of it. It'll be easier. Yeah, there we go. So we're doing the exact same thing as above, except I'm only taking a couple of the classes. And for each of these different classes, I'm taking all the images of 4, all the images of 5, all the images of 8. I'm just going to calculate the mean and then run PCA on all the 4 images, on all the 5 images, on all the 8 images. So when we do that, we get the principal components, and then I'm reconstructing the quote-unquote principal components to just be viewed as an image. I'm just laying it out. It's like a vector. It's a vector of 780 some odd numbers, but I'm reconstructing it as an image, same way as to match the input images, to match the dimensions of the input images. And when we do that, we see that the projection vectors, the eigenvectors, with the largest eigenvalues, they are pretty cool. They actually bear a lot of they're looking for features of the commonly handwritten digits. So we see the biggest eigenvector is all the digits written almost exactly, like properly, upright, and all of that. Then we have other projection vectors that account for slants, and then we have other projection images that account for all sorts of other weirdness. So yeah, it's kind of cool. It's kind of cool that you could view, eigenvectors and eigenvalues seem like this sort of nebulous, just mathematical construct with no real practicality, but it's doing a very real physical thing. It's just looking for patterns in the inputs, and it's looking for, and the largest eigenvalue, this vector is looking for the most common pattern. This vector is looking for the second most common pattern. This vector is looking for the third most common pattern, et cetera, okay? But of course, we segmented the data so that we only looked at PCA for 5. So we only did PCA on all the 5s, and PCA on all the 4s, and PCA on all the 8s. If we didn't segment the data, if we ran it on the entire MNIST data set, and then looked at all the eigenvectors, we see that the biggest eigenvector looks a lot like a 0. And so if we look back at our graph, at our scatter plot, we see how nicely 0 is segmented from the rest of the graph. I mean, that's a pretty cool indication. Basically, what we're seeing is that, using PCA analysis, it's a lot easier to recognize a 0 compared to any of the other numbers. Then we use this second amalgamation that sort of looks like a 2. It has components of all sorts of numbers. It has components of 7, it has components of 2, and if we look at the second vector, we see that 2, where is 2? We see 2 is interspersed here. We see 7 is all here. So we see that the digits that look most like these eigenvectors basically are the information. Their features are maintained best. Which is, I mean, I mean, that's what we've been doing, right? That's literally that whole mathematical thing, that's what we wanted to do. But it's nice to see it. It's nice to see it visually. Yeah, so thanks to the pattern recognition book for giving me this idea. Anyway, okay, so I think we've all had enough of sort of mathematical derivations, so we could end it here. Next week we're going to discuss k-means clustering. Homework 7 is due Monday. Homework 8 will be posted tomorrow. The project, I promise, I know I keep saying this, but it's coming by this weekend. There's like one out of the 3 topics is just giving me problems, and I don't want to abandon it, but it's been way too long. So either I'm going to abandon it or post whatever I have by Saturday. We'll see. But it will come this weekend. And it's just going to be like a slightly longer homework. So it's not going to be too intensive. But you'll see then. All right. Thank you, guys. Have a good weekend. Oh. See, I forgot one. Mo's. Oh, man. This is what I get for writing lectures at 3 in the morning. All right. Have a good weekend.
May I have a very quick question? So will you post a lecture recording for the past 2 and this lecture?
Oh yeah, I will. The lecture recordings, I think on the site, it's just the link that's missing. But the lecture recordings are on the MediaSpace channel. So on the site there is a link to the MediaSpace channel. But yeah, I'll post the links in the actual table also. Yeah,
Can I show you something?
yeah, please.